Hey engineering students, welcome to the first video of week 8. And in case you're wondering, this is a 17-week semester, so we're pretty much halfway there right now, and the end of the quarter is going to be coming up soon. Alright, a little bit of housekeeping first. I recommend that you don't click turn in with your documents and spreadsheets if we do another assignment like this, until you're actually certain that it's all done and you've got it, you've watched both videos, you've gotten any help from me. As far as I could tell, it looked like that once you click turn in, that you couldn't access it again once you had done that, and I had to go back and re-give access, which I wasn't expecting. And I'm fine with doing that, but I think, yeah, probably it's better not to turn in until you're completely done. And in this last week, you definitely had to watch the second video if you wanted to get it all done properly. So don't be too anxious to jump the gun and do it after the first video. You really couldn't have done it unless you just really read and understood and worked hard, and maybe you did. I want to spend a couple minutes here at the start just going over the answers to the basic centroid assignment. Okay, so if you did the advanced one last week, you would have seen a different shape. This is the one that the younger students had. If you're a younger student, this is the one the older students had. It had 4 shapes in total. So I just wanted to walk through this one as an example to both. I feel like we need one more display of how this works before we get really settled in. So I've already set up the table. I don't have any formulas anywhere, but I do have the table set up just to save some time. And I think you should lay it out exactly like this. You don't have to create your own format, your own layout or anything. I'm trying to show you what I think is the easiest, most optimized version. So, alright, I split mine into 2 shapes. I had a triangle on top. I think it's obvious where that starts and ends. The base of that triangle was a width of 6 inches. Notice again, only numbers in these cells, all units up in the column headers. The height of my triangle was 4 inches. Notice you really got to read the scale. In this case, every square stands for 2 inches. In the advanced assignment, each square happened to stand for 1. That's just the scale that I chose to use. Alright, the rectangle has a base of 10, that's pretty straightforward, and has a height of 4, also very straightforward. Area calculations equals 0.5 times base times height. That's the basic formula for a triangle, and we get the preview of the answer hovering right there, 12. Enter. Alright, for the rectangle, equals, I'm not going to use the suggestion because it's a rectangle, not a triangle. It's simply base times height. And then for my sum, I think I will use the sum formula, even though there are only 2 elements in there, but that's fine. We like it. Get a preview of the answer, 52. Alright, now that we were doing all the way from the very first video, so that's very straightforward, in my opinion. The centroids of the individual shapes, I absolutely agree this is where it gets a little trickier. So just to remind you, this is X subscript I is how you're supposed to read that, and Y subscript I. These are the X and Y centroids of the individual shapes. Now the X centroid of the triangular shape. So what this is like, if you think of the centroid of the individual triangle as being a little dot on the page, and the origin is in the origin at bottom left, as we have been doing it in all of these examples, because it usually makes the most sense. If you picture like a little dot right there in the middle of the triangle, we're really trying to give the X and Y coordinates of that dot. Okay, that is what this is. So we say that it is going to be, there's a few ways we could do this. We could say, all right, it's going to be the base of the triangle, of the rectangle, the 10, and then minus 1/3 of remember multiplication means of, 1/3 of the base of the triangle. That might seem like a really complicated way to do something that's fairly simple. So if you just looked at the diagram and typed in 8, that would be just fine. We know the centroid is always 1/3 in from the thick end of a right angle triangle, or alternatively 2/3 in from the sharp end. Now because our triangle clearly has a base length of 6, that means 2/3 of that would be 4, or 1/3 of that would be 2. So you could just kind of work out that it's 8 meters along from the origin. But I am choosing to define it in terms of what is already there, because if the diagram changes, this formula will update automatically. So that's why I put the length of the rectangle minus 1/3, because now I'm going back from the thick end, 1/3 of the base of the triangle. Let's stay on with the triangle firstly. The y coordinate, now some of you asked about this. Why do I add a 4? It's because the triangle doesn't start from where the x-axis is, like down the very bottom. It's like offset. The triangle begins 4 units up from the bottom of the shape. So I have to add on that 4 before I do my my 1/3 of the triangle's height. And I'm doing 1/3 because the triangle's thick end is on the bottom, not the other way around. So that is what we get. The rectangle's x and y coordinates for its centroid are much more straightforward. It's simply half of the base, it's like halfway along, and it's half of the height. And it is that simple because there's no offset involved. Because that rectangle happens to be aligned right perfectly with the XY axes and the origin, that's why that's as easy as that. If it weren't, I would need to introduce offsets, but I don't. Now for the total centroid, remember what this was, referring back to the formula in the book, we need to multiply all of the x centroids by the areas, and then add all those products together. In this case, there are only 2 products to add together. Okay, we add up the triangle area times xi product, and we add up the rectangle area plus xi product. And then we lastly have a denominator. We divide by the total area. And that is our result. And then you might remember, I'll use it in this one, I also told you there is another cool formula where instead of doing those manually, you actually just sort of drag select the columns that you want to multiply together and then add. It will sum those products. And then we still need to divide by the area, but the end result there is no different than the one I manually did. Alright, those are our answers. That's how we got there. I hope that was in some way helpful too. I'm going to switch over to the whiteboard now, and we're going to talk about the next topic, which is moments. We will return to centroids and areas throughout the year a little bit. I am kind of compacting this whole thing down into more or less one semester, but the centroid of the tables and desks and things that we're making is really important, because we know that the center of mass is going to be somewhere near the middle of that, like somewhere around where that centroid is, and that is going to be very critical for knowing whether this thing is going to tip over. Is it safe? Especially if you have like things that fold out. If you have a computer that extends out, you've got to keep track of that so that it is just not going to tip. That's one very practical use of the centroid. Where is that weight force acting? Is it safe? Is it supported by the base? So hope you can understand that. And we'll try to use spreadsheets more. Some of you really enjoyed this, judging by your comments. So that's awesome. All right, let's switch over to the whiteboard. Now, as we get started here, I want to call out to Eliana. want to say great job, Eliana. You're the first person to submit your furniture concept model. Eliana used some Lego, and she designs a desk for Mrs. Jones. It's got some little folding, like standing desk things that kind of like flip up and flip down. She has like two independent ones. It's a cool design, and yeah, I look forward to seeing all the other ones. Make sure you remember this is only about an hour's work. That's all it's supposed to be. Just read the directions. Don't go overboard, but make sure you're doing the things I'm asking for. Okay, here's a little bit of background for you for our lesson today in moments. We have this thing that we all know about called Newton's second law. Now you should know very well that Newton's second law is given by either F equals ma, or alternatively, if you rearrange it, A equals F over m. That's the same exact thing, just has F or A as the subject. Algebraically no different. And what this says is that forces produce acceleration. Now, because I've been talking to you guys about sigma notation as well, I can actually supplement this a little bit. I'm going to put a sigma in front of these F's. Just showing what we really mean is that the total amount of force, the total or the sum of all forces will produce acceleration. Because it is possible to have forces, but they balance each other. So the sum of the forces is zero and then there's no acceleration. I mean, that's what statics is all about, right? Sigma F equals zero. Doesn't mean there are no forces, it just means that they balance. We can also go a little further because you guys know more than the average physics student in high school. We know that some of these things are what? They are vectors. Mass is a scalar, doesn't have a direction, but force and acceleration absolutely always have directions. That is what they are. They are vectors. Now, while it will never cease to be true that an unbalanced force will produce an acceleration, it's also true that there's other stuff going on as well. Most forces, at most times, are actually doing two things. Okay? First of all, they're trying to cause accelerations. And I say they are trying because they often get cancelled out by other forces. They kind of fight back, and then you don't get an acceleration in the end. But all forces are trying to cause accelerations, and forces are also trying to cause rotations. And we have not talked about this at all so far. We've talked about things that have been like sliding accelerations, as though that's all things ever did. They just like slipped and slid around like boxes on ice, and that's just not the case. Things are always rotating, they're flipping, they're turning. Machinery, your body, like all these things just couldn't function without rotating as well as translating. Okay, translating is the opposite to rotating. Translating is when you slide. And that's the whole topic of this. That's what the reading is for this week. It's all about moments. Moments are that extra situation where the force is trying to cause a rotation as well as the acceleration. So let me define some of the language. For some of you, this will be old hat and just a little refresher. For some of you, this is brand new and you've never seen it, never heard it before. All right, let's see. So first of all, a moment is defined as force times distance. Okay, force times distance. Now I will say, even right here from the start, there are some different symbols for moments. Sometimes people use the Greek letter tau. You could use X instead of D, but I'm just going to stick to this. It's what our book uses, and it is probably the most common one. But the idea is that it's force times distance, which is not too hard, right? You can always multiply two numbers, force in maybe newtons, a distance in meters. Actually, let me give those units to you. So you could have in the SI unit system, which every time I say that, I want to say it a different way, because when you say SI, that stands for System International. The S is the system, so you can't have the SI system any more than you can have an ATM machine, but that's okay, or a PIN number. You know what I'm talking about. So you've got force is measured in newtons. You have, yeah, I'll write it here, force measured in newtons. You've got your distance D measured in meters. Don't forget, the metric system includes centimeters, kilometers, millimeters, and so on. And then, oh dear. And then you got your moment itself, like what gets produced, the M in the formula. That is measured in Newton meters. Because if you're going to multiply a Newton by a meter, force times distance, you have to end up with Newton meters, newtons times meters. And we absolutely do not break down the Newton into its constituent components. Those who do this a lot in like chemistry and stuff, you guys know that Newtons have something behind them. They are a derived unit, but when we don't cancel them out, we just let it be. In the US customary system, force is measured in pounds. Distance will either be in feet or it can be in inches. I wouldn't say there's one preferred over the other. It depends on what you're doing. If it's a smallish situation, it'll be inches. If it's like a big, like a skyscraper situation, it'll be feet. And so what you end up with is usually spoken of as foot pounds, and most Americans write a little dash, a little hyphen, maybe a dot, or inch pounds. And don't ask me why. In the SI system, we always say Newton meters. We never say I can't even say it. Meter newtons? Wow, that sounds terrible. But in the US system, no one ever says pounds feet. We always put the distance first. No one ever says pound inches. Oh, look at me. I'm looking in his textbook on page 157. He has pound inches. But I've only ever heard people say verbally inch pounds. But there you go. I think all that goes to show you that the American system doesn't have a lot of tight constraints. It's kind of like regional varieties wherever you are. SI system, the whole point of that was to standardize things across the entire planet Earth, and only America resisted. All right. Another quick note here is that for those who are interested, I'm going to put this in red because this is just for the older students who are caring about it. A moment is a vector, and it is produced by the cross product of the force vector times the distance vector. Okay, a few of you have asked about this when we studied vectors in the discussion boards. There are cross products, there are dot products. The dot product is more simple, the cross product is more complex. The cross product takes two vectors. Okay, let's say you have like the force vector and the, how can I show this? Here we go, we'll just put it right here. And the distance vector. And then the moment vector that gets produced is actually perpendicular to both of those. And yeah, it gets complex. Just trust me. Just be glad that we're not actually doing that. But To work out the simple number is easy enough. You really do just, as I have in the black there, just multiply force times distance. But I wanted to point that out because some of you are interested. That's a cross product. It happens in 3 dimensions. Okay, now how do we show moments? I'm going to get rid of that. There we go. How do we show moments? We really have 2 options, and they're both mentioned pretty well in the book. We have the curled arrow method, and then we have the double-headed vector method. So I don't know if you had a better name for it. I'm calling it the curled arrow system, and then you had the double-headed vector. And in the diagram on page 150, you can see he has a curled one there, and then he has the same vector. Okay, make sure you realize he's trying to show the same vector. That's what the equal sign is between them. That's on page 150, and he's trying to show that that's 2 alternate ways to show the exact same thing. And I want to point out something here. He doesn't mention it until later, page 155. But matching those 2 things up and saying that they are the same thing as each other, that follows something called the right hand rule. Now, the right hand rule is kind of fun, and it's fun because you'll see engineers all sitting busily taking their mechanics, statics exam in a crowded lecture hall, physically distanced, of course, and you'll see all these engineers all waving their right hand around, twisting their right hand around, trying to understand the problem they're working on, because your right hand actually really does help you. What is the right hand rule? Well, it is this. It says that if you can imagine, well, I'm not going to have you imagine, I'm going to draw it. If you can get your right hand there like that. Wow, that's kind of a weird bendy finger, but you get it. Okay, so imagine doing this with your palm. If you want to do it right now, you may do it. Oh, that hand's getting worse as I go. So you're curling your fingers around. Imagine you're holding a spear or something with your thumb sticking out, or you're hitchhiking, but your fingers are slightly opened up. So the right hand rule says that, I'll switch to the blue, that axis of rotation passes through your open hand. And by the way, I'm going to explain more about axis of rotation very, very soon. You can either draw it with a double-headed vector, which points in the same direction as your thumb. Okay, that's one option to draw it. A double-headed vector pointing the same direction as how your thumb is pointing. Or, in the green, you can do it with a curled arrow which follows that curl that your fingers are making right now. Okay, that's all it says. Actually, there are several right-hand rules in engineering. Your right hand is incredibly useful. But this is the one for drawing rotational vectors, okay? Again, either your thumb is the double-headed vector direction, or your fingers are curling in that direction of motion, in that curled arrow variety. All right. So yeah, if you're wondering what he's talking about on page 155, that is that, page 155. Okay, I know I'm kind of jumping around here. I'm just sort of hitting things as they make sense in the flow of explanation. So let's talk again more here. We said that a moment is a force times a distance. What is the distance that we are referring to? Okay, forces I think we understand pretty well. Like a force is a force, of course. And you push with a force and there it is. But you know, when it comes to distances, you got to decide, what distance am I measuring? What is that distance? Is it the length or the width of the object I'm pushing on? Is it something else? So what it is, the picture on page 151 with the door is simple, brilliant, makes a ton of sense. I'll kind of re-sketch it here, slightly more simple. It's a door with hinges. You gotta, well, he didn't do the doorknob, did he? I'll do the doorknob. There you go. And what we're saying is that if you come up to this door and you push with a particular force, okay, vector F, let's see, I'll do it in purple. There is a distance. Actually, I'm not going to do it dashed as though it is not a real thing, because this is the other vector. This is pretty important. So we're talking about this vector right here. Let's get this right. Okay, I'm actually not certain which way the vector head should point. It's okay. But this is the distance that we're referring to. Okay, it's a distance vector. And the really, really important idea is that that distance vector is going back to the axis of rotation. Important word for today. Okay, axis of rotation. It is the distance from the force you applied back to your axis of rotation. And here's the other really important thing too. That force and that distance, they must be, let's see which color, I'll do it in green, they must be perpendicular. That's me trying to show a right angle on an angle, like looking like kind of with perspective, okay? They must be perpendicular to each other. In fact, sometimes we even draw a little symbol above that moment diagram, sorry, above that moment formula, m equals fd, to show, I think I did that a few videos earlier actually when I was talking about vectors. That's a little symbol to show perpendicularity. See, it's like a little line coming out of another line with a right angle between them. If your force and your distance are not perpendicular, they actually don't create a moment. They just don't. More on that later, but just take that as a true thing for now. Moments are only generated when the force and the distance back to the axis are perpendicular. Now, what the author is showing on page 151, he's showing that that distance and that force, that's really the only thing that matters for the creation of that moment. You know, that moment is that tendency to want to open or close this door, that tendency to want to start rotating. He says you could get that exact same force and you could apply it right here. I'm trying to draw the exact same one, okay? That's what that is supposed to be. Or he says for some reason, I don't know why, you could crawl along the carpet and apply the exact same force right here. It does not matter as long as you are the exact same distance back to the axis, back to the axis of rotation, and of course that those two things are perpendicular. Okay, all three of those, whether you push at the top, push in the middle, or push at the bottom, if you can really produce the exact same force, not more, not less, and it really is still perpendicular, then bang, you'll get the same outcome. The door will swing at the same exact rate No faster, no slower. In fact, the door won't know any difference. Gets the exact same thing. And then he's also shown as well with a curled arrow that moment exists. I'll actually draw it on the diagram. I'll just do it right here. I'll go whoop, right there. Okay, that is our moment. And we draw it like centered on that axis of rotation. Now the axis of rotation, so that's the place around which the object wants to turn. I think with the door that's incredibly obvious. It's where the hinges are. That's how a door turns. It turns on its hinges. There's even a proverb about that. As a door turns on its hinges, so does a lazy man in bed. All things that are rotating and turning have some axis of rotation. It might not always be as obvious as a set of hinges that are all aligned perfectly, but there will always be one, and you get used to spotting those pretty quickly. Let me give you some other examples of moments with this force times distance idea and the perpendicularity and all of it. There you go. Let me just remind you once more. You don't have to do it every time. I'm just reminding you. Let me show you a child on a seesaw. Okay, you've got a very simple seesaw. It's the safety kind with the handles, and the kid is right there, holding on. Look how happy that weird looking bald kid is. Looks a little like an alien actually. And that child sits in that seesaw, and that child has a particular weight. Okay, it has a weight force. I'm getting kind of particular this lesson, aren't I? I'm actually showing those vector arrows a lot more. It has a weight force. Remember that weight is calculated by multiplying what two things was it? Weight equals, do you remember? M times G, where G is the vector of acceleration, gravity acceleration, and M is the mass. So this young child has a weight vector which concentrates approximately right there, and there it is. Like that's a force. It's a weight force in this case, not an applied force like a force of pushing or pulling. And there is absolutely a distance. It's this distance back to, I hope you can intuitively sense that this point right here, that is the axis of rotation. Okay, like that fulcrum. We can't really draw the dotted line in this case because I did a 2D diagram, and the axis of rotation is coming up out of the page at us. Okay, it's like an imaginary hinge line, and so there's just nothing more I can do except show a dot on that 2D diagram. If I kind of like rotated and showed this thing in, you know, like a perspective drawing, then I could do that like in the last one, but this is fine. This is very, very acceptable. So I'm going to have in this case that weight force times that distance force. Those two are definitely perpendicular, no doubt about it. So like maybe our kid has a mass of 40 kilograms. Okay, we know that G is 9.8 meters per second squared. So quick little calculation here. Okay, so his weight is 392 newtons. The distance, I don't know, I'm just going to make it up. Like I made up the 40. The distance, you know, might be like, maybe it's a 2 meter distance to the center of that seesaw. And so that means the moment is F times D, the weight times D, 392 times 2, 784 Newton meters. Let me just show it to you in US customary units, like a similar thing. Let's say the kid has a mass of, I don't know, 3 slugs. I remember we got kind of caught up on these slugs and pounds and all that nonsense. G in US customary is 32.2 feet per second squared. So in this case, M times G is 96.6 pounds. Let's say our distance here is 6 foot, which by the way is approximately 2 meters. So in this case, our moment is going to be 96.6 times 6 is 579.6 pound feet. Okay, so all I'm adding to this today is just the fact that we're multiplying a force times a distance. You already had looked at doing weight calculations in both metric and SI. But yeah, that's an example. And so again, that moment, we could show that, did I use a particular color? I used red. So we could show that, in this case, as a moment like that. Again, we can't really use the double-headed arrow because it comes out of the page. We can't really see it. So the curled arrow makes the most sense. And notice the way that arrow is curling. It's curling in the natural direction that we are expecting the seesaw to move. We expect the seesaw to rotate, what would that be, like to the right, okay, as the kid goes down. Right side down, left side up. And so that's what that moment arrow direction is doing. Okay, it's just a way of like summarizing that action down into one curled arrow with an actual quantity as well. Okay, that quantity of 784 Newton meters or 580 pound feet. By the way, in case it's not totally clear, I made up numbers that didn't correspond for those two. I just picked round numbers for both. Don't walk away thinking 784 Newton meters is the same equivalent thing as 579.6 pound feet. It's not. Okay, give me one more example for you of a moment occurring in like, you know, real life, as it were. Think of an aeroplane coming down out of the sky. I hope you've had the pleasure of some airline travel in your life. I've probably had a little too much airline travel in my life. I'm ready just to kind of stay home, I think. I am gonna kind of get fancy, I guess, with my drawings. Some little bolts or something. Don't really know what they are actually, but they look like stuff that exists. Okay, so there's an airplane wheel. It's coming down out of the sky. It's, you know, it's about to hit the ground, and when it does strike the ground, there is a sudden like bang, like a friction force, and it happens right here at this particular point, bang, right there, that point of application. This is like a force of friction. You can do a better job than that. Okay, it's a force of friction that strikes the wheel. That's the impact with the tarmac. And we have a center of rotation and a distance. Here's that center of rotation. It's right there in the middle. It's a wheel. We kind of feel very naturally where that center is. And so here is the distance right there. Okay, distance from the force application to the center of rotation, and here is that perpendicularity, which we have continued to emphasize. The moment is for some distance. So maybe that force of friction is like 10 kilonewtons, like a massive bang. Maybe that distance is, not very much. It's an airline wheel is not always huge, depends how big the plane is. So our moment is that force times that distance. 10 times 0.5 is 5 kilonewton meters. Okay, or if you prefer, 5,000 Newton meters. If I show that now, I would show that moment with the curled arrow like this. Okay. It's a 5 kilonewton meter curled arrow right there, centered on that center of rotation, pointing in the way that we're expecting that wheel to spin. Which, with a little bit of thought, you can see why I picked that direction and not the other. Okay, so there you go, three examples of how moments might appear in everyday examples: doors turning, children on seesaws, aeroplanes coming into land. By the way, did you know that when Americans basically invented the first aeroplanes, even here in America, they were called aeroplanes, not airplanes? Fun fact. The Wright brothers referred to theirs as an aeroplane. Okay, what I want to say next is that all of these examples, these all feel like very active. Okay, like things are moving. You've got airplane wheels spinning and children bouncing on seesaws and doors turning. But we are doing statics, right? Where the sum of all forces equals 0. In fact, I could even add something today. Not only do the sum of all forces equal 0, but in statics, the sum of all moments also equals 0. Equals 0. The sum equals 0. So not only are things not accelerating and sliding around, but they're also not rotating. Okay, your building that you build is not rotating. Your desk, which you build, is not rotating. If it is, something's wrong. We don't want it to. So that's like the second half of the coin, and I never say that one up front like I do with sum of forces, because we don't really know much about moments yet, but both those things are perfectly true. Let me give an example of how the moments can cancel out in a statics situation. I'm going to draw a few. It's an odd example, but I think it makes sense. Okay, this is a metal pole, maybe a stop sign. Okay, just for something that we're very, very familiar with. It's sunk into the ground, and I want you to imagine someone pulling sideways on it. Okay, someone is grabbing the pole, let's say right here. There you go, a little point of application. And they pull sideways, just like that, with a particular force. Is this stop sign going to move? Is it going to start to rotate, like the seesaw, like the aeroplane wheel, like the door? Well, no, at least we hope not. But we do have a force that is perpendicular to a distance. And you see what I'm doing here? I'm kind of assuming that if you can imagine this thing moving, we would imagine it moving probably right there at the, like the place where the ground begins. It might not be absolutely true, but it'd be pretty good. Yeah, I guess a pretty good approximation. So we could use that quite safely. Maybe it's like a 3-foot distance. Maybe this force is a 20-pound force. Just to make up some numbers here to help you out. So we have all the elements. We have a force, we have a distance, they're perpendicular, it's all there. But we know from experience that unless you pull really hard, or you grab your truck and throw a chain around it, that thing's not going to move. It's not going to either accelerate due to a force, due to an unbalanced force. It's also not going to rotate due to an unbalanced moment. So what is actually happening here? we actually have what I might call a resistance moment, and we also have resistance forces. Okay, we already looked a little bit at resistance or reaction forces. So we also have moments doing the same thing at like when things are planted in the ground. So that's all I want to say about that. But so like this is still a static situation, even though there is a moment being created, even though you can calculate what that moment is. It is 20 times 3, it is 60 pound-feet in this case. So there is a 60 pound-foot moment. So what we know is that there must be like a negative, oops, I did the opposite, didn't I? There must be a negative 60 pound-foot moment in the ground resisting so that the total moment equals 0. All right, I want to start to wrap up because we're getting to the end of our time. I will quickly call out to the idea of force couples. It is mentioned on page 152. And force couples are very common and they're very useful. Let me just explain that passage, and you can obviously reread that. But let me try to say it to you verbally as well. This is just the idea that we often, even instinctively, produce two moments at the same time when we are turning something. It happens all the time. We turn stuff with our hands. He gives the example of a steering wheel. Okay, and we naturally push one direction and pull down in the other. And I'm using the same letter because they are the same thing. He actually used negative F. I didn't like that because he already drew the arrow going the other way. So personally, I'd rather that he let the direction do the talking instead of trying to doubly say it with a negative as well. It happens when if you think of like, look at the top of a faucet for like turning on water. When you grab it with your hand, again, you very naturally like have some fingers pushing on one side and others on the other side. It happens all the time. And what's really cool about this is that the sum of the forces in situations with force couples is that the sum of all forces is 0. You have the exact same force, F, pointing in exactly opposite directions. Therefore, the sum of forces is 0. Therefore, that means you get no acceleration, like no sliding acceleration, no translation. Like, in other words, to say it more plainly, the steering wheel doesn't start sliding across the car. The faucet handle doesn't start sliding across the room because you pushed on it. Now remember, when you push on free objects, they're supposed to start accelerating if there's an unbalanced force. But this has a balanced force. There's two forces. They match. They're a couple. So there's 0 net force. However, although there is a 0 net force, the same is not true of the moment. That's a cross through the equal sign to show that not equal to. The moment exists. There is a moment. Okay. There is going to be a moment that turns that steering wheel that way. There is going to be a moment that turns that faucet handle that way. So we get the necessary motion of the moment, to turn the object we want to turn without any of the inconvenient sliding of accelerations, which in these cases we don't want. And he also points out in this case, to get the magnitude of the moment, you should use this distance. Okay, just use that total gap between the two forces and then you multiply that times one of those forces, not both, just one. Okay, the moment in this case is force times distance, just as it always is. But we're not like adding those two forces together. We're just picking one of them and multiplying it by that total distance gap between them. They are still perpendicular. Okay, everywhere you look, things are still perpendicular. So we're being very consistent with all that we're doing. I can get into more detail individually if anyone wishes as to why we just string across between the two forces and call that the distance. Maybe put it in the discussion board if you want to ask me, but I'll just agree with him for now and we'll leave it at that. Okay, that's it. Keep on building your concept model. Look out for the assignment this week. Just remember that you will be able to do some of it right now, but you'll probably only be able to finish it after you watch the second video on Thursday. Okay, thanks a whole lot, and we'll see you guys around.